Now, one cool use of infinite limits is how we can use them to find vertical asymptotes. So asymptotes in general, just as a reminder, are those lines that approach the graph of a function indefinitely. So the lines could be vertical, horizontal, or slant, meaning they're not between, they're not vertical nor horizontal, so something in between at an angle. We're going to see how to calculate vertical asymptotes now. So the first thing that I need to notice is how that information translates algebraically into a limit. So let me graph what I'm trying to say. Let's say you have this graph here. Let me maybe split this up. Have some a here, and if you want to say that x equals to a, this is the line, x equals to a. If you want to say that, so let's say number one, that the limit when x approaches a from the left is plus infinity, you're actually saying that the graph behaves like this. We're going up indefinitely when x gets closer and closer to a. What happens here on this end doesn't matter. We're looking at this end. We're getting closer and closer. As long as this is plus infinity, then we're good. If it were, let's go back a little bit, on 2, if the limit when approach a from the right is plus infinity, that also works. So that's what 2 says. And on 3, we're saying x approaches a from the left is minus infinity, so we're going down like that. And on 4, we're saying x approaches a from the right is minus infinity, so we're saying that. In all these 4 cases, we have x equals a as a vertical asymptote. So these are the only ways how I can have a vertical asymptote. In the end, we're trying to see when the function value is very, very large, and if we have a denominator involved, we're trying to see the denominator be 0 and the numerator not be 0, or at least not small enough. We can, instead of listing all these 4 possibilities, it can be sort of lazy, mathematically speaking, and write this with the plus or minus symbols instead. As long as you understand that we just, when we take the plus, we can take the plus or the minus, and when we take the minus, we can take the plus or the minus either. Either of the 2 or 4 possibilities will work. So let's practice this on this example on A. So how we can find the vertical asymptotes for the following function? We're looking for infinite limits. We're trying to make this infinite. And as you see, as you remember, this only happens when the bottom is very small and the top is not as small. So let's first study the bottom. This will be, let me rewrite that, x squared minus 4x. So let me maybe just begin with the denominator. I think this is it's going to be more organized. So I'll say the denominator, x squared minus 1. I make that equal 0. That's x squared. I can factor it. X minus 1, x plus 1. This is the difference of squares, right? A plus b, a minus b. So that's either x minus 1 equals 0 or x plus 1 equals 0, which gives x equals 1 or x equals negative 1. So these 2 are possibilities for my asymptotes. So possible, and I'll be more specific, possible vertical asymptotes. How do I check? I got to do the limits and see. The limit when x goes to 1 and the limit when x goes to negative 1. I can do them one-sided. If one of the one-sided limits work and make it either plus or minus infinity, that's going to be fine to give me an asymptote. At least from that side, but that will be fine. So let me do that now. Let me try and see the limit of f of x when x goes to, let's say, 1 from the left. Why not? This will be, and if I factor the top, I will get, so on the top I have 2 numbers that multiply to 3 and add to 4, so that will be x minus 1, x minus 3, I believe that will be. Bottom, like I said, x minus 1, x plus 1. That allows me to cross these out. Limit when x goes to 1. There's no 0 happening there, right? As you notice, the bottom no longer contains a factor of 0. That's just going to be a minus 2 over 2, so just a minus 1. It's not going to be infinity. So x equals 1, and this is going to happen from the left and from the right, if you notice. So this is not going to be an asymptote. I'll even not determine whether I was looking at the limit from the left or from the right. I'll just remove that because the calculation is going to be exactly the same. Now I'll try x equals minus 1. So what's the limit? X goes to minus 1 of f of x. I'll do the exact same calculation, but when I get to the end, I'll have x plus 1. If I try and plug in minus 1, that's going to be 0. So if, for example, I decide to do it from the right, let's say, I'll have the top being about a minus 1 minus 3, so about a minus 4, and the bottom being, okay, something bigger than minus 1. Okay, so x, let me do it a different color so you remember what I'm doing. X is bigger than minus 1, which means x plus 1 is bigger than 0. This bottom here is positive, but still very, very small because they're very, very close. So this will be something small positive. So this implies that the limit minus 1 from the right is going to be minus infinity. So x equals minus 1 is the vertical asymptote. There's only one this time. Okay, so it's not enough. We found the 1. It's not enough that the denominator equals to 0. You also need the limit when x approaches that value to be plus infinity or minus infinity from either side. It doesn't have to be both sides. One side is enough. So let's try that on B. See what happens there. The only possibility for us to get a 0 at the denominator of g would be x equals to 2. So the possible vertical asymptote is x equals to 2. So we're going to see what happens when we find the limit of g of x when x approaches 2. I factor the top. I have a 2 and a 1, right? That's the limit. X approaches 2. X minus 2. X minus 1. X minus 2. Cancel these two. Remember, I can cancel because x not equal to 2. So it's just very close. So x minus 1. So that's just a 2 minus 1, which is just a 1. So there are no vertical asymptotes. Even though the bottom equals to 0 at 2, the limit does not equal to plus or minus infinity. What's happening here, and you saw that the limit equals to 1, right? If I were to graph this guy at 2, y equals 1, I'd have something approaching this, but actually undefined there, so like a hole. And the same thing would happen at A. So if you were to graph this guy, let's go back at what happened at A. So again, this is B, this is A graphically. The limit when x approached 1 was minus 1. So we'd have minus 1. 1 would have a hole in here. But we did know that minus 1 was a vertical, x equals minus 1 was a vertical asymptote. So if I put a minus 1 there, this is an asymptote that we're not allowed to touch. So when x approaches 1 from the right, the limit is minus infinity. So that means this is happening here. But then whatever happens This goes back, and we have a hole in there somewhere. I don't know exactly if the graph is like this, like the behavior in between, I'm not sure. But I know that here, this is precisely what happens, and here, this is precisely what happens. Maybe I'll highlight so you know that I'm sure about this, and I'm sure about this, but the rest could connect in any way. Same thing here, right? I'm sure about what happens around x equals to 2, but not anywhere else. And if I wanted to know what happens on this side of the asymptote, right? I'll maybe use a red pen there. What happens in here? I'd have to do the limit for x approaching minus 1 from the left, like changing this. And I guess that that would be a plus infinity. I'd guess that that's plus like that. But again, you'd have to check. So add a question mark there. Okay, C is our last. What happens when we handle the tangent? So the tangent, or excuse me, the cotangent. Got to remember that the tangent is the reciprocal of the tangent. So the cotangent, instead of sine over cosine, is cosine over sine. So we treat it the same way when a sine x equals 0. Remember, we solved in Math 142 in the pre-calculus classes. This is a pre-calculus skill. We solved trig equations. When is the sine equal to 0? If you look at the unit circle, sine is the y-coordinate. The numbers that have y-coordinate equal to 0 are here and here. Y-coordinate equals to 0 on the circle. So these are 0 radians or pi radians. But that actually repeats every 2 pi. So we have 0, pi, 2 pi, 3 pi, 4 pi. All of those are possible locations for vertical asymptotes. And they're not even the only ones we could have. Minus pi, minus 2 pi, minus 3 pi. Don't believe me? Just plug in those into a calculator, or just try and locate them in the unit circle. What's the sign of minus pi? All of those are going to be 0, right? What we're going to have as consequences for these, though, is that if you remember the Pythagorean identities, it says sine squared x plus cosine squared x equal 1. At all of these values, we're going to have sine squared equals 0. So 0 squared plus cosine squared x equals 1. So that will mean cosine squared x equals 1. So cosine is plus or minus 1. So when I try and calculate the limit, x approaches, let's say, one of those, let's say pi, for example. Doesn't matter if it's from the left or from the right, I don't care. The cotangent x, that will be x approaching pi from the right, cosine x over sine x. We're going to get either plus or minus 1. In the case of pi, I know what it is, right? It's going to be minus 1. But let's just pretend it's plus or minus 1. I don't really care. And the bottom will be either 0, negative, or positive, right? Like plus or minus a small thing. So it doesn't really matter what it is. It just matters that the answer is going to be plus or minus something big. Okay? So I could even say, instead of using pi as an example, I could even say this is A. Because it's going to happen for all of these values. For any of these values, the same thing will happen, because the sine will be 0, the cosine will be either 1 or minus 1. So we're going to have for any A value. So asymptotes are all at multiples of pi. So I'll say that the vertical asymptotes are x equal to k pi, where k is a whole number. So this is it. This is how I calculate and find vertical asymptotes for different types of functions.